Hi everybody, I'm Gergely Pongrácz, working at Ericsson, and I'm actually the technical coordinator of the Hexa-X-II project. We are leading this project together with Risa Papajani from UvA, University of Amsterdam. And basically the slogan for the project is Programmability and Secure Distributed Intelligence for Real-Time End-to-End CG Network. You can see the contributors in the project. We have a quite healthy balance, I would say, between industry, academia, small and big companies as well. You can see the basic facts. I will not delve into the details. From a technical perspective, it's not that important. And I think the first important question probably is that why do we have Hexa-X-II at all? We have a lot of 6G related projects these days, so why another one? And I can say that the basic difference probably is that we focus pretty much on end-to-end programmability, network programmability, and we try to study how it can solve the challenging use cases that, for example, Joachim described in the previous presentation or in the Hexa-X presentation as well. So as we have a network which have to accommodate multiple services, this is a study between flexibility performance. This is the usual trade-off, and we are studying that how well can we do it if we employ network programmability. And also we are studying the complexity problem of centralized control versus distributed control. So how can we make this optimization slightly more decentralized and still being accurate enough? That's another, I would say, story that we are studying. And then, of course, we have a lot of kind of other techniques that are quite familiar today for many of you, like AI methods, blockchain. So we actually try to also study how these technologies could contribute in building a better 6G network, basically. In a nutshell, I would say that the project is more like system architecture focused. We have a more bottom-up view and realization/development focused than the rest of the EU projects, at least the projects I know about. So these are the main differences, I would say. So having said that, what are the key innovations in Hexa-X-II? The first is, as I said, this data plane programmability. And you can also see the partners on the slide. I will not go into these details. The secure multi-agent based network control is the second key factor, I would say. We have privacy preserving monitoring as well. And of course, we have intent-based orchestration and lifecycle management. A few words about the architecture and the architectural layers. On the top, we have the intent-based orchestration layer, as I already shown in the previous picture, which I will come back to the details to some extent at least. Then we have an optimization and network control layer, and then a programmable data plane layer, and then the physical infra layer. And in this presentation, I will mostly focus on the programmable data plane layer and how we make it as cloud native as possible. Okay, but a few words about the services. The Hexa-X-II is trying to focus on how to describe services in a kind of simple enough fashion. And it's not very surprising that the easiest description is probably the service graph. And I think we have one more addition that we can define edge-to-edge or end-to-end services as well. As you can see on the picture, an edge-to-edge service means that pretty much like what we have today, so that you can specify your network path between the user equipment and the mobile gateway, and you can guarantee some things on that link, basically that segment. And the end-to-end would mean that you can actually have full control over the end-to-end path, like latency, bandwidth, these type of things. And that is probably a bit more complex, but also gives you more control. So basically, we would like to make an architecture or develop a system that can support both at the same time, basically. Okay, so some architecture details, and especially some processes that we think we will have in the system. As you can see on the top, we have this more real-time thing that is managing the life cycle of the services. And basically, we want to use intent-based mechanisms there, especially for service creation. We have this traditional way to have SLAs and then generate the configuration out of the SLAs. And we want to make it a bit more automatic. So we want to use the SLAs and use further intents like policies, whatever, that can be translated into the service configuration automatically. And then these service descriptions that will be generated will be populated into the catalog. And then later on, if you want to actually instantiate a service or deploy a service, that's fairly easy because you already have the service description basically in the catalog that you can use. Then the next big part is the service orchestration part, which pretty much means the service graph creation. Also the graph splitting, because the SMO is the central entity. It knows pretty much everything about the network, and the resources, and the topology and everything. So it will be in a perfect position to split the actual network graph, the service graph, and then communicate with the lower layers, with the site-specific layers. The next thing is the multi-agent system, which is for the real-time optimization or near real-time optimization, I would say. And it basically have components both in the central domain and in the site domain, in every site. On the sites, you would run the agents that would collect the data that are needed for optimization. And in the central area, you have this orchestration engine for the actual agents. And you also have some central monitor collecting, like basically some database-like feature. Most of the work is typically done by the agents, especially the near real-time work is typically done by the agents. And there you actually do the trick with AI-driven decision-making and things like that. Then, the last large block is the programmable data plane. Here we are basically talking about quite flexible, customized packet processing. In this project, we are using the P4 language as a kind of a description language for the data plane, but the architectural choices and the solutions are not P4 specific. And what we are aiming is basically a very cloud native like behavior in the data plane, which was not there, not even in 5G, I can say. And I will tell a bit more about how we actually try to achieve this kind of cloud nativeness in the data plane. So basically, one big block for the transparency, or one solution for the transparency would be to actually split the network functions into a control plane program part, the IML part, which is the infrastructure management layer. It's kind of a enhanced hardware abstraction layer in our case, or hardware/network function data plane abstraction layer. And then we have the data plane program as well, which is, I think, fairly obvious for most of you who actually worked with data plane programs so far. As I said, you can use multiple languages to actually describe the data plane behavior. So what is this infrastructure management layer? That's probably the next question. So basically, the IML is responsible for this data plane transparency. That is pretty much the key element in the network function aggregation, disaggregation, also the adoption between the different domains. On the picture, you can see that we have a transport network, for example, which is most likely not Desire 6G capable, so it will not be able to understand the headers we are generating and we are using and things like that. So there you need some adaptation logic. And also a lot of other features that I will describe a bit later, like load balancing, heavy hitter detection, and things like that. So when you want to deploy a service, in that sense, so I think probably the most important thing is that services are typically specified in a logical view. So what kind of logical components you will need to have, these network functions or maybe application functions you will need to have for that given service. And that's actually a logical view. So you start from some site, go through some chain or graph of the network functions, and you arrive to some destination. But this is like an end-to-end thingy. But when it comes to real deployments, you have to make assignments to the site-specific resources. And first of all, you need to specify the sites that you want to use based on location, based on policies, based on some other factors. That is done by the SMO since it has the knowledge about the sites. And then once you are done with the site selection, you download the necessary information to the site-specific IML logic, and then it will do the actual physical deployment. So basically, these are the steps you can see on the picture. First, you do the site selection, site allocation. Then you basically allocate some extra network functions that will do some other things like load balancing or adaptation logics or actual network function routing, things like that for you. But this is actually an automatic process. It is populated by the IML automatically. The application developer or the network function developer doesn't need to actually describe these steps. And then the final step is the physical mapping, where you have the resources on the site, and then you map all of your network functions, whether they are business logic network functions or infrastructure automatic network functions. They are populated to some software or hardware element. Okay, these were the basics, and let's jump a bit into the cloud-native-like data plane, unified cloud-native-like data plane. So what are the mechanisms that we want to use and why? And actually, the first slide is about the why. So there is a softwareization trend in the data plane, and it used to be only in the core network for a few years, but now it's also in the RAN. So the examples are, of course, softwareized packet core, like basically or product in Ericsson, for example. And also Cloud Run is a good example for that. So the main things is that we want to achieve that it has a lot of flexibility and good scalability, because you can easily increase the resources. So there are a lot of promises, but of course, there are a lot of drawbacks at the same time. For example, unpredictable latency. When it comes to a software platform and a CPU platform, these are not designed for this packet processing, and especially for this bounded latency or low latency packet processing. Although they can do a pretty nice job, actually, in average, I would say. Then we have throughput limits, where we have components that has some bottlenecks. And typically we are using, these days at least, we are using kernel bypass techniques, because those are more powerful when it comes to packet speed and when it comes to deterministic behaviors. If you have to go through the kernel, you are not that good. It's actually getting better, but you're still trying to avoid the kernel if you are developing data plane programs. And also, when it comes to a CPU system, you typically end up with higher energy consumption and maybe increasing OPEX, but probably to some extent CAPEX is better, but OPEX is typically higher. These are interesting questions. There are a lot of pros and cons. I will not go into the details of that. But basically, this is the reason that the industry is talking and also developing quite many hardware accelerators for this field. And basically, you can say that if you go up towards the CPUs, then of course the abstraction programmability increases. But if you go down, then performance increases. So there are some certain trade-offs in this field. But it's not that straightforward, because the big problem is that these hardware entities are typically very much focusing on performance, and they don't really support cloud-native integration. You have these low-level tools and APIs that are bare metal APIs, and it's very hard to use these in a cloud-native system, I would say. And our answer for that is basically using this P4 language. To some extent, that's an answer, but of course, you need to be more open to other aspects. So basically, I just wanted to present that, of course, we have a shared infrastructure. At least we envision to have a shared infrastructure where you try to run your workload partly on software, partly on hardware. And of course, as I already showed you, the network services are defined on a fairly abstract level, a very high abstraction level. Actually, it would be very nice to decouple the implementation from this high abstraction. And that is exactly what we try to do in the DSR-6G programmable data plane work package. So basically that will mean that if you have two user equipment, one is with high throughput demand, the other is with low throughput demand, those will be handled slightly differently in the network. So most likely the high throughput demand will look for as many hardware accelerations as possible, while on the low throughput demand user, you're not caring that much because it can be easily sustained on a normal CPU. I think I already mentioned most of these features of the IML. We are starting to say that the IML is a cloud-native data plane manager. So it provides a simple logical view to the controllers and to the external world, basically on the northbound interface. And then below that, it hides basically these automatic things like load balancing, heavy hitter handling, and auto scaling and things like that. So just to have some example for that so that you can easily understand. So one of the big problems, especially in the hardware pipelines, is that what happens if you want to do this multi-tenancy on a hardware pipeline, where you actually have these shared resources, typical ASIC resources, but you want to have some kind of traffic isolation, at least on the logical level. So for that, basically, we have this PDP aggregation proxy, which is part of the IML layer, and it works as the following. When you have a new network function that is coming to that hardware switch or that hardware block, you add the network function data plane to the multi-tenant program. You precompile and download it to the switch. And basically, you also download instantiate the control plane, like the proxy part of the control plane endpoint to the proxy. And then you instantiate the control plane somewhere else. And then the control plane will talk to the proxy. It won't talk directly to the switch itself, but it will talk to the proxy. And through the proxy, it can actually have this vision of being alone, basically. So we can do this separation, this multi-tenancy separation, that the switch itself is not capable of. So that is one example. The second example would be load balancing, which again it's an automatic feature of the system. So if you have like data plane instances, you can instantiate multiple data plane instances, then you can basically have a load balancer, which is, I would say, an infrastructure function. And then your control plane still talks to the proxy, and it still talks to a kind of a virtual data plane. It won't really see that you have multiple instances running below. So it would be pretty similar to like a Kubernetes system where you have a load balanced service, and you don't need to know exactly how many instances are running out of from that service. So we would like to mimic that behavior in this kind of more hardware-centric world. And then we have another example is the heavy hitter offloading with the hybrid hardware. So let's assume that you have multiple data plane implementations, network function implementations, that one can run on the hardware block and another is basically a software implementation. And the hardware block is typically very much resource constrained. Only a couple of thousands of users or maybe a couple of 10,000 of users can be progressing through the hardware, and the rest should go through the software basically, because there you have much more memory for your tables. And then this would be nice to have an automatic process for that surveys what user is the heavy hitter and then moves the data accordingly and the payload accordingly. And that is exactly what we are trying to achieve with the heavy hitter proxy and the heavy hitter offloader in this case. Basically, we would like to have these seamless migrations between the different hardware blocks. And yeah, I think these are almost all are in development. So the architectural questions are mostly, I would say, solved. These are almost under development or just started at least. So we will have some more results in a few months. And then we have started some preliminary thinking that, okay, if we have this description of the services, then what about moving some of the like 3GPP specific functions into the architecture? Because, for example, part of the UPF is handling this service identification for the users. We have to map the users to services anyway. And having said that, we know where the user is on a site level at least. So we can use these two information basically to make it part of the infrastructure and make it more automatic in a sense. But these are just preliminary thinking. So we just started to think that what are the implications of having such a more automated data plane in our hands? So what can we really benefit? Maybe this is not a good idea, maybe it's good, we will see. Okay, I think that's the last slide. So as I said, I think the main message is that we try to say that simplicity and high performance are okay together. And in CG, we probably need both. Having said that, of course, simplicity is good because it leads to high performance, so they are, of course, not enemies. But also achieving simplicity for certain use cases, I think this is important. And we have to keep in mind that we have multiple use cases in our system. And we don't want to overcomplicate the system just to be able to handle multiple use cases at the same time. So I think for that, having this cloud native like behavior in the data plane helps a lot. And we will see how the automatic, like this KPI management system, this mass system would also help. That is, I think we started a bit later, so we know more about the programmable data plane at the moment, that it has a lot of promises. But of course, the intent-based SLA handling and the multi-agent system also has a lot of promises, I would say. So having said that, thank you very much.